This is a re-recording of the information from the GPM-GLOBE Student Field Campaign Introductory webinar due to technical difficulties recording the original webinar. What I'll go over today is an introduction to the Global Precipitation Measurement mission, some resources to use with your students and events during the campaign, and a brief review of data collection and data entry. So to begin with, why do we need to look from space? We have rain gauges to measure the rain on the ground, which are very useful but not evenly distributed over the Earth. You can see in the diagram on the left, all those yellow dots are rain gauges that are around the world. However, there are lots of gaps in between those, and there are none in the oceans. All those yellow dots you see there are on islands. So we're really missing a lot of data if we only use rain gauges. If you actually took all those rain gauges and put them all together in one place, you would have, they would only fill up about 2 basketball courts, as you can see from that right-hand image. So you might ask about radar. Ground-based radar still doesn't cover everywhere. You can see even in the US that has pretty good coverage, there are a lot of gaps, and it doesn't extend very far out of the ocean, over the oceans. So really the only way that we can get a complete picture is to look via satellite. So we have the Tropical Rainfall Measuring Mission, which was launched in 1997 in a partnership between NASA and JAXA, the Japanese Aerospace Agency. And it was the first satellite that had a precipitation radar. You can see that 3-dimensional image of Hurricane Sandy in the lower left. But the problem with TRMM is that it only has a range of 35 degrees north to 35 degrees south. So we're getting the tropical rainfall extent, but we're not able to follow storms such as Hurricane Sandy that become extratropical storms. So you can see the line there. TRMM could not watch Hurricane Sandy as it actually made landfall. So what NASA decided was necessary, and JAXA decided was necessary, was an improved satellite that would be able to measure precipitation over a larger portion of the globe. So these are some images of the construction of GPM, which was the largest satellite built to date at Goddard Space Flight Center. It's described as being as heavy as a private aircraft, but only the size of a truck. So it's a very massive and very large satellite compared to many. They built it at Goddard Space Flight Center, but then it was actually launched by JAXA in Japan. So you can see in the middle picture there, they loaded the satellite into a shipping crate, and it barely fit aboard the largest Air Force cargo jet they had. They took it and put it in the top of a rocket fairing, which then was loaded on the top of the rocket to be launched. And the satellite was launched at 1:37 p.m. Eastern Time, which was 3:30 in the morning in Japan, on February 27th of 2014. The core observatory has 2 primary instruments that can look at precipitation in different ways, and they're more advanced instruments than TRMM had aboard. The first instrument is the microwave imager. It has 13 different channels that are each sensitive to different types of rain, snow, or mixed rain and snow. So it can get a better picture of what type of rain and snow is falling in a particular area. The other instrument then is the dual frequency precipitation radar. So TRMM was the first precipitation radar in space, and now GPM is the only satellite currently. TRMM and GPM are the only 2 with precipitation radar. And those 2 boxes that you see there on the bottom of the satellite are the radar. And what that allows the satellite to do is actually see 3-dimensionally inside storm clouds. So it's sending out an active pulse that bounces off the particles in the cloud that then bounces back to the satellite, and the satellite can tell exactly where in the cloud those particles are. And it can also tell whether they're rain particles, snow particles, large ice particles, whatever it is, it can figure out what it is. So one way to think about it is that the microwave imager is like an X-ray showing where there's heavy rain falling, like the bone densities you would see on an X-ray, whereas the radar is more like a CAT scan that gives us a 3-dimensional image of not just where bones are, but if they're the picture of everything that in between and exactly where in the body those parts are. GPM is not just the satellite itself. The mission actually includes a constellation of satellites. So one satellite like GPM takes about 90 minutes to orbit the Earth once, which means that you can cover the entire Earth every 3 or 4 days. But if you combine the data from a constellation of satellites, you can actually get greater increased time coverage, so you can get data about any particular point on Earth about every 3 hours, in some cases even less. So GPM is in a sense the concert master for this orchestra orchestra of satellites. It tunes the instruments that are all similar, but not exactly the same. It tunes the instruments of all these other satellites so that the data can be combined and create this global picture of precipitation about every 3 hours. And you can see it's a very international mission, lots of countries participating either with satellites or with other investigations, other joint projects. These are some of the first images that GPM released from a storm that happened March 10th. You can see in the upper right, these areas of red are areas of heavier precipitation, whereas the areas of green on the outside are lighter precipitation. And that's from the microwave imager through these 13 channels that I mentioned before, each of which can detect a different type of rain or snow or mixed rain and snow. And then on the left is some of the first images from the precipitation radar. Again, those red areas are showing areas of high intensity rainfall, but with the radar, you can see where, not just the geographic area, the map area where the precipitation is heaviest, but actually where in the cloud the precipitation is heaviest. So you'll notice that the bottom part of the cloud, those red areas are near the surface. That's where the heavy rainfall is, whereas up higher in the cloud, it's showing lighter precipitation. One of the neat things about GPM is that it's actually able to estimate both liquid rainfall and snow. TRM's satellite instruments were more focused on heavy rain, not the light rain, and they were not good at snow at all. It was focused on the tropics. It wasn't necessary at the time. But GPM has new abilities to measure snowfall. So you can see on the left the microwave data images from a snowstorm on March 17th. And then on the right is what's ground truth from some ground-based instruments. And you can see that they don't completely correlate. They're still working on making sure that GPM's algorithms, computer algorithms for processing the data are optimized, but you can see that it's actually pretty close. It's showing basically what's being seen on the ground. But this also points out the reason for field campaigns like the one we're about to embark on. You really need to measure from the ground and from space and do the ground validation or the ground truthing to ensure that your algorithms are working appropriately. A little bit more about ground validation. These are some of the ground validation campaigns that the GPM scientists have done so far. You can see each one is looking at a different type of precipitation. And there's actually one coming up that is not yet on this map. 2015, there will be a campaign in the Olympic Peninsula in Washington State looking at some of the mountain areas and effects of mountains on measuring precipitation. And then there's our permanent ground validation facility at Wallops Flight Facility. And we will have a webinar in February focused specifically on more details about the ground validation and the official campaigns that GPM has done. So the purpose of a satellite like GPM is really to measure the precipitation, but we want to use that data for something valuable for society and for societal benefits. So these are some of the areas of societal benefit for GPM. And I'll go through a few more detailed examples of some of these, but really you could do, and we will actually have a webinar more about societal applications coming up in April. So there really is, you could have an individual webinar on any of these particular topics, but I'll go over at least a bit of an overview. So one of the primary ones is looking at severe storms and hurricanes. You can see in the upper right just how much improvement you can get in terms of tracking storms based on having satellite data. So this is from Hurricane Bonnie in 1998, and what they did is they entered data into a model to predict the storm, and they did two runs. They did one with TRM data and one without TRM data, and then compared that to the actual storm track. And you can see this green line here is the one without using TRM data. And the purplish line here is with TRM data, which is much closer to the actual storm track, that red line. And that's really important because we want to be able to warn people where the greatest risk for hurricanes is, and if they are in the path of hurricanes, what steps they need to take. So being able to see from the satellite is really important to be able to track these storms. And then again, as I mentioned, GPM's orbit being a little bit farther north and south, so GPM's orbit extends to 60 degrees north and south, actually 65 degrees north to south, compared to 35 degrees for TRM. That means that with GPM we can actually track storms further away from the equator than TRM was able to. One example of a recent storm here, this is what became Tropical Cyclone Makalah. It started out as a tropical depression. You can see not particularly organized, a few areas near Guam of heavier precipitation. But then on the right-hand image, you can see it's starting to become more of the traditional hurricane or tropical storm shape. And again, some areas of even heavier precipitation. And we've also got the three-dimensional radar data in there, so you can see what's happening in different parts of the storm. And that was between January 12th and January 14th. And then on January 16th, it actually became the first Western Pacific typhoon of the year before hitting the Philippines. And you can see, again, we're starting to get more of that traditional spiral shape of a hurricane in some areas of very heavy precipitation, as shown by the precipitation microwave imager. And then you can also on the right see accumulations. So on the left is actually rain rate, millimeters per hour at a particular point in time that GPM was going over the satellite. But then on the right is accumulations for that week of January 13th to the 20th. And you can see areas that received a great deal of precipitation during that time frame. So this ability to look inside storms is really amazing. So this is looking inside Hurricane Katrina. And those red towers are what they call hot towers or convective towers. And scientists believe that those towers, when you see those towers, that can indicate the storm is going to intensify within the next 12 to 24 hours. And sure enough, Hurricane Katrina did intensify shortly after this data was taken. And GPM and TRIM are the only two satellites up there with this precipitation data that allows us to see inside storm clouds. So we can help, the satellite data helps us improve the tracks of hurricanes, but also helps us look at the intensity and when hurricanes might intensify. Some of the other applications, of course, once you have rainfall from a storm or hurricane, you also can have then problems with landslides, and you can use satellite data to help predict areas of landslides. You combine the data of precipitation, rain accumulation and precipitation rate with information about topography and soil type and soil moisture and various of those sorts of things, and then you can create models that can potentially predict what areas are at risk of rainfall triggered landslides. One recent example was the hurricane in Oso, Washington in March of 2014 that unfortunately did cause fatalities and a number of houses to be destroyed. And if you look at the data on the right, this is from TRIM data. Each of those blue lines represents a year of rainfall accumulation between 2000 and 2014. The red line is 2014 itself. So if you notice that 2014 started out to be on the dry side actually in terms of rainfall accumulation. All the way through, it was among the driest through December. Then if you look at January through February, it was actually the driest of the last 14 years, but then suddenly around the middle of February you have a steep rise in the amount of rainfall, and then the 2014 ended up as the third wettest year in the last 14, which then led to this unfortunate disaster. But you can notice that it's not even just one particular rain event. In this case, it was suddenly the season became much wetter overall, and there were numerous rain events saturating the soil and creating a higher probability of a landslide occurring. Another reason we need the precipitation data is to be able to model climate and weather. So that top image is an images of a hurricane, and you can see labeled the eye and the eye wall. And again, the red areas is heavier intensity rainfall, and the bluish areas are going to be lower intensity rainfall. So by having more data about precipitation, we can plug it in to improve our weather forecasts. And then many people are concerned about how climate is going to be changing, and precipitation is one of those things that we know is going to change, but we need more information to see how that's going to change. Some areas are likely to get wetter, some are likely to get drier, but we need the global picture of precipitation to be able to have appropriate data to enter in these models and see what's going on and monitor what's going on. An interesting one that you might not expect satellites to have much impact on human health and diseases, but it turns out you can actually use precipitation data, satellite precipitation data, to look at diseases and track certain diseases that have a component of related to the weather and the environment. So, for example, on the left there, you can see observed plague cases in Uganda, and overlaid with the precipitation data from TRMM, and the cases are associated with wetter and cooler regions. On the right is a diagram of the life cycle of the schistosomiasis, well, spread by snails in Ethiopia, and they've found a relationship between when the rain occurs and floods the field, people walk around in the fields, and then the snails transmit this disease to them, and then they can once they see the rainfall, they can then predict that after the incubation period of the disease, they're going to need to have clinics prepared with the proper treatment. And this is based on looking at satellite precipitation data. So that's what I just finished giving you as kind of a higher level, adult level description of GPM and what it does. But I have also prepared a student level presentation that's available on the GPM-GLOBE website and under documents, and that there is a presentation that is available for you to use with your students. I'm going to go through a small part of it just to show you. There's the whole thing. Each of those slides on the PowerPoint does have notes underneath of points you can discuss, and of course you feel free to modify and adapt this as suitable for your needs. Shorter, longer, adding things, taking things away, whatever is appropriate to use with your students. So just a bit of this presentation. I mean, the idea is really to get kids to think about precipitation. What is it? Why is it important? Why does it matter? Do we have enough of it? How can we know if precipitation is falling? If we aren't sure we have enough, how can we measure it? And so just looking at some of the applications and some of the reasons why precipitation and precipitation measurement is important. So why do we need to measure precipitation from a satellite in orbit above Earth? This is a really great video that we have on our website called For Good Measure that goes through all that. It was a good one for students. Can talk about the satellite. I've talked about a few of the instruments that are there. Of course, the satellite also needs solar panels so that it can power its instruments. There's a propulsion module, reaction wheels that aren't really visible in the back, but to adjust the satellite in its orbit as needed. Avionics and star trackers. The satellite needs to know where it is in space so that it can adjust its position properly. And then, of course, we need an antenna to be able to send our data back and to get instructions from the ground. And we also have additional resources available if you want to take a more engineering focus with your students. We have various models that you can build and some additional resources available on our website also. So how will the students actually be involved? The idea is that the satellites see precipitation, but it's different from the way we collect that information from the ground or even ground-based radar. So that's why we have to do this comparison. You can't rely just on one or just on the other. You need to compare them. And so that's why we need data from the ground. So scientists do these field campaigns. This image is from a field campaign in North Carolina they're called ground validation, where they set up an array of rain gauges and then compare the data to the satellite, or before the satellite was launched. They had similar instruments in an aircraft. They'd fly over the field. And so with the rain gauge you and your students are going to use at your school, you can become part of this ground validation team, sending data that will then compare to the satellite in a similar way, and also to other networks of rain gauges, and really see, how is this working? Is our algorithm right? What patterns can we notice? So the idea is to collect data from February 1st to April 15th, collecting it through the GLOBE website and reporting it through there. Now, obviously, if you can't manage every day, that's fine. You can do multi-day accumulations. If you think you're not going to be able to start until March, please still submit your data. We'll take your data, but we want to make sure that it is not an added burden. So please try to do daily if possible. But if you need to do multi-day accumulations for the weekend, or if you miss for whatever reason, still report the data. We still want to see it. We have scientists working with us that are going to take the data and compare it to the satellite's data, as well as data from those other networks of rain gauges and radars. And then, of course, the idea is not just to have the scientists having all the fun, but to have students doing their own analyses and doing using data from other schools and from their local area, and looking at climate averages and asking their own questions about what is happening with precipitation. And one of the key messages is we know the Earth is changing, but we need to be monitoring it. And that's one of the things that NASA is really committed to, is monitoring how our Earth is changing. And just one of the key things for this with students is you can find examples of extreme weather anywhere around the Earth, whether it's droughts or flooding or landslides or whatever it is. Precipitation and precipitation extreme events affect everybody on Earth at some point or another, and so it's really a good way to be relevant to students if you can find some local examples of how precipitation has affected their area, your area, in the past. So a few more educator resources. We do have our precipitation education website. That's actually one of those, that Lego model there you see front and center as one of the models that I mentioned, that if you're wanting to go a more engineering focus. There's an introductory video there on the website that gives you a tour how to find things. I've highlighted a few that are specifically suited to this field campaign. Those are available in the Student Field Campaign Teacher Participation Guide, which is also available under the Documents tab on the GLOBE GPM Community on GLOBE. One resource that I will highlight for you, the Rain Gauge Design Challenge. This is one where you have students use recyclable plastic bottles to try to build an instrument that could measure precipitation. And the idea is not that they build an accurate rain gauge, but they actually think more deeply about how rain is measured and why it's important to have standardized instruments, and really just give them a chance to do an engineering design challenge about something that they will use that the official rain gauge to take measurements. So you can see here's some examples of the kids. The materials off to the left, I tend to do this very open-ended, just say here's your materials, build a rain gauge. You can have them do it independently, in groups, however you prefer. And then of course testing is an important part of the process. You can test inside, you can test outside, using a watering can of some sort, or put it out in the rain next to your official rain gauge and do some comparisons that way. I mean, you can see that so it gets interesting if you start having snow and students have to think about, well, maybe my rain gauge works for liquid precipitation, but I might need to come up with something different for snowfall. And just getting kids to think about those questions and how this all works is a good place to start. We will have a webinar specifically about how to get and use data, including the IMerge data, which is the merged data from all of that constellation of satellites that just got released in the middle of January. We will have a webinar about this coming up in March, is I believe when that webinar will be. Some examples, though, briefly, you can get GPM precipitation data in Google Earth. This is the most recent precipitation data, but it is possible to get older precipitation data if you're looking for historic averages or you're looking for a past event. One source of those climate averages is my NASA data. You can get the data as a map. You can get it as a data table. You can get it as a different types of graphs. You can get it also as a Google Earth overlay as well from my NASA data. So that's one source. And again, we'll have more resources about this in the upcoming webinars and further as we proceed in the campaign. I would also encourage everybody to please join our GPM-GLOBE community. That's where we will have updates and discussion boards that we really want to get you involved in this. Here's our list of our webinars. The webinar on February 2nd will be aimed at students, so there'll be short webinars throughout the day to tune into with your students that will just give kind of the brief version of this, and then hopefully some question and answer depending on how many classes join in. February 18th, we'll talk about ground validation and satellite measurement, and we'll have some guest scientists for that webinar. March 18th, talking about data and how you can get data and how you can use that data with your students. And then April 15th, satellite data and extreme events, how we use this data for societal applications. So the February 2nd webinar is geared at students. The other three are more geared at teachers, and information about more detail about these and registration links are on the GPM-GLOBE community page. We'll have blogs posted, so every Monday starting February 2nd, various topics: ground validation, accuracy of rain gauges, snow measurement, analyzing data, various applications, and those you can get to all of those on the GPM page, the overview tab, and then blog posts. Just a brief review of data collection. If you haven't already set up a site, of course you want a site away from trees, buildings, and other structures. You can see the rain gauge on the left, with the funnel, measuring tube, overflow tube, mounting bracket, all that sort of thing. It needs to be a location your students can easily access, and that sometimes can be a trade-off. The ideal data collection location may not be actually the best place for a rain gauge, but if you put it out in a perfect place and then never make measurements, that's not so good either. So you just have to balance that. And by the way, for any of these things, there's always the Globe Help Desk. You can contact me via the GPM website or via the GPM community on Globe. But if you have any questions or concerns about any of these things, please, there are resources available to help you. So if you haven't added an observation site, if you go to globe.gov, the main page, and enter live data, you'll see you'll see a list of your school. This is the school where I used to teach, so that's why it's still up there. And you can see there's a place there to add a site, which will pull up this site definition page. Some basic details: latitude, longitude, elevation. Give your site a name. If you choose atmosphere as a site type, it'll give you the option to include a little bit more information. If there happen to be any obstacles you couldn't avoid, the surface cover, a little bit more information. Reading the rain gauge. Of course, you want to do it within an hour of solar noon, and there's resources available on the Globe website and online calculators to help you calculate solar noon. But pull out your rain gauge tube, read the bottom of the meniscus, that nice curved bit, and then estimate to the nearest millimeter. One thing I know some of our U.S. teachers have rain gauges that measure in inches, so just make sure that you convert before you enter that into Globe. And there is a data sheet available on the GPM GLOBE website. I think maybe there's my next slide. So if you do have a rain gauge that measures in inches, you can use this data sheet on the right that prompts you to remind you to convert it before you enter it in Globe. If you want to do other observations besides rainfall, there's the integrated one-day data sheet there on the left that has other observations you might wish to make with your students at the same time. So those are the two data sheets that you can use. For actual data entry, again, you're going to go to the main Globe page and then enter live data. And one thing that has confused a few people, there is nothing that says precipitation as an option. You need to go to that integrated one-day data choice, and then that will allow you to enter precipitation as well as a few other things. But if you're looking for precipitation on that first page under the atmosphere, it doesn't say it directly. You have to do it. It's a two-step thing, and you can bookmark that and save that so you can get to it without as many clicks. But then there you get to your data sheet that you can enter how many days you've accumulated. Again, ideally every day, but if for some reason you miss a day, you can do a 2 or 3 day accumulation. Types of precipitation, you click on whatever type of precipitation, and then it allows you to enter the amount of precipitation you have received. We'd love to have you contribute to the discussion board. Here's one that would be a great place for you to post some testable questions and some questions that your students have come up with in terms of how to use this data that they're collecting and that other schools are collecting. So please check into that discussion board and contribute there. And so if you want more information about TRIM and GPM, there's our websites. Follow us on Twitter or like us on Facebook. There's the link for the GLOBE community page that will allow you to, and that has more resources. And then, of course, on the GPM page, there's a contact button that you can always get a hold of me, or through the GPM page I'm listed there on the blogs. You can find my email, and if you have any questions, also the Globe Help Desk is a great resource as far as that goes. So please, if you're having any problems with this, please get in touch with somebody. We want you to participate. We want you to submit your data, and we can help you as much as possible, as much as needed for that. Thank you for tuning in for this webinar, and I'll look forward to seeing you on February 18th about ground validation.